So far, we've shown how to convert maximum a posteriori estimation into terms that you can actually train a model with using data. Let's not forget that the ultimate goal is to train a model which generalizes to examples not seen during training. So what does it mean to generalize? Is there a way to measure generalization or at least estimate it? To this end, we'll introduce the idea of generalization error. Suppose we look at the space of all possible data points with labels and sum up the errors of our predictions over that space. This would be a good start, except most of the data points within this entire space don't make sense or are improbable. For example, if we were working in the space of labeled images, we likely wouldn't come across a data point with an image of a dog with the label dolphin. Instead, we do a weighted sum using the joint probability of observing the data together with the label as the weight. You may recognize the integral of some term multiplied by the probability as an expectation, and this term is the expected error over the data points. As an example of an error function, we can use squared error, which gives a measure of how wrong our predictions are for a regression task. We can use different error functions for different tasks, and they don't necessarily have to be related to any of the terms we train our model with. Before continuing, let's introduce a notion of a perfect model H, which maps input from data distribution X to label distribution Y. It is deterministic, so it will always produce the same output for a given input. H maps X to desired Y perfectly, with the exception of some noise epsilon in the labels themselves. We'll assume the noise has expected value 0, and the label Y is H's prediction plus epsilon. Let's start from the generalization error integral and rewrite it as an expectation. For this particular derivation, we will take the error function to be squared error. Now we substitute in the perfect model H plus noise epsilon for Y. As shorthand, to make the calculations easier to follow, we'll rewrite h of x as h and f sub theta of x as f. Multiplying out the inside of the expectation gives the following. Expectation is linear, so we can separate the sum terms into their own expectations. Noise epsilon is independent of h and f, so we can split it out as shown, and note that the expected value of our noise was assumed to be 0, so the terms containing the expected value of epsilon vanish. Since h is deterministic, the expected value of h is equal to h, and similarly for h squared. We'll now use the identity that the expected value of quantity f squared is equal to the squared expectation of f plus the variance of f. This comes from rearranging one of the common ways of writing variance in terms of expectations. We can rewrite the first three terms as quantity h minus expectation of f and quantity squared. Finally, we use the same identity mentioned before to rewrite the expectation of epsilon squared, and note again that the expectation of epsilon is 0. Examining the resulting expression, we have broken out generalization error for squared error into these three terms. The first term represents how much our predictions are off from the perfect model's predictions on average. So there's a notion that some component of our generalization error may come from systematic mistakes made by our model due to how the model works. Maybe we use a model that can't quite capture the structure of the data properly, and therefore results in the errors here. We refer to error that comes from erroneous assumptions in the learning algorithm as model bias. The next term tells us the amount of error due to sensitivity to details in the training set, and we refer to this as model variance. This type of error doesn't come from erroneous assumptions in the learning algorithm like bias does. Instead, it's from the fact that we train using only a subset of all of the data and are trying to generalize from that. There may be irrelevant details or noise in the specific data used for training that don't hold in general. The last component is unavoidable error due to noise. Remember, we assumed that even the perfect model could only perform perfectly up to some degree of noise. Although this derivation was specific to squared error, the concepts of model bias and variance hold in general. If you use other error functions, you should still end up with some terms that correspond to model bias, some that correspond to model variance, and some from unavoidable noise. Understanding what contributes to model errors and how to reduce or trade off bias and variance will give you an idea of how to improve any models you train. We will use some sample data to see examples of what high bias and high variance can look like. This data was generated by adding normally distributed random noise to a cubic polynomial. This polynomial will serve as the perfect model. So if we look at another set of data generated the same way, but this time in red for clarity, we see that the predictions this model would make are still good. If we fit a straight line to the blue data, we've made a bad assumption in the model we fit. You may imagine this will lead to a lot of the error in our predictions being due to model bias. We assume too simple of a model, and this leads to systematic errors. We call this regime underfitting, where we have high bias and it results in us not learning to map inputs to outputs properly. We could also take a very powerful model that fits every data point we train with perfectly. Here we expect a lot of the error to come from model variance, which, as you may recall, is error due to sensitivity to details in the training data. We call the regime where we have high variance overfitting, where we have overly fit to details in the training data. The predictions may not seem too bad in this visual, but it's clear that there are points for which the errors come from the fact that we fit to the blue data. There are more extreme cases of overfitting where it's even more clear that this is undesirable, but hopefully this illustrated the point. Depending on the source of the errors your model is making, you may want to try different techniques to reduce bias or variance. What are some of these techniques? Well, some ways you can reduce bias are to double check that there's nothing wrong with how you're gathering or processing the data that will introduce systematic errors. You can also add in extra information or features to the data that help your model predict the labels better, or make the model more complex. To reduce variance, you can gather more training data, use a less complicated model, use explicit or implicit regularization, or do feature selection or dimensionality reduction on the data, which essentially will keep the most important information in the input data and limit the amount of noise we can fit to. If we had perfect model H, we could directly calculate bias and variance, but in most cases, we don't. And if we did have it, we would most likely just use it instead of training any other models. Since generalization error is an expectation, we can approximate it using Monte Carlo sampling. This means we estimate it through simulation. We typically use a calculation using data to estimate the error. But we must be careful in how we do this, so we get an actual estimate of generalization performance. Remember, we can overfit to the training data and in the extreme case, we may even perform perfectly on the training data, but very poorly on everything else. So we need a sample set of data from the distribution of data we expect to see at deployment time. It should be drawn independently of the training data, and we call such set a holdout set. This name comes from the fact that typically, instead of gathering a whole new set of data, we will split a data set that has been gathered into training data and sets that will not be trained on or held out from training. It is important not to look at or tune any parameters or hyperparameters using the final holdout set used to estimate deployment performance. Even running evaluation and going back to model training could throw off the estimation, since you may implicitly make different choices with the information you've gotten from evaluating. If you need to tune hyperparameters or want to test changes to your algorithm, you may consider splitting out another set called a validation set. This set is helpful in estimating model bias and variance. But again, since we tune algorithm choices and hyperparameters using this set, it doesn't give true estimation of generalization performance, which is why we still keep around a holdout set. The intention is for the holdout set to mimic actual production data as closely as possible. For clarity, production refers to the environment and running of the model in actual applications. So if data evolves over time, we may keep the most recent data as the holdout. As a side note, we do allow any transformations or pre-processing for the model that you can do at prediction time to this set as well. As some last points, you may hear the holdout set be referred to as test set and the validation set be referred to as the development set. This is not the only way of doing data splitting. There are also techniques such as cross-validation that handle the data differently, but I won't go into those details now. So using our training and validation data, we can estimate performance on some metric during development. Given a perfect score on the metric is A, perfect model performance is B, training set performance of our model is C, and validation performance of our model is D. We can see indicators of high bias or high variance. Remember, we don't necessarily have the perfect model, and we may not know what its performance is. For this, we may make a guess at it based on human performance or by digging through the data to estimate the amount of noise in the labels. Any difference between A and B will be a result of unavoidable noise. Differences between B and C will give an estimate of error resulting from model bias. Finally, differences between C and D will give an estimate of error resulting from model variance. As a note, these comparisons only help when the data in the training and validation sets are from the same underlying distribution. If you do any artificial rebalancing of the data, or mess with the data distribution in any of the sets, the numbers may not be comparable. If you do rebalancing of both train and validation sets, you may also consider having an additional set without any of these tweaks to help you verify that any improvements on validation performance actually results in performance gains on the distribution of interest, what will be seen in production. Let's look at a couple examples. The metric here is MSE, mean squared error. Here we see a large gap between perfect model and training set performance, which is an indicator of high bias, and so we may want to try some bias reduction techniques to improve the model. Suppose we retrain and see the following. Now there's still a large gap between train and validation performance, which is an indicator of high variance, so we can try variance reduction techniques. There are also scenarios where it may not be clear if there's a lot of bias and variance. Maybe this model is good enough for use depending on your requirements. If not, you can still try to reduce bias or variance depending on what seems most promising. In general, it's a good practice to reduce bias first and overfit your model a bit to prove that the model is capable of performing the task sufficiently well before scaling back and doing variance reduction. So far, I've been showing a lot of examples with mean-squared error and regression tasks, since that's what's been covered so far in the videos. But note that we can also look at different metrics for different tasks and use them to determine what to do to improve the model.